Okay, so in this video I'm going to be talking about kinematic equations. I'm not going to do any examples with them. I'm just going to be showing a derivation of them and where they come from. So the base differential relations are derived in this way. So you have time t, position x, velocity v, acceleration a. V average, the average velocity, is x of t minus x of t sub 0 divided by t minus t sub 0. That gives you delta x over delta t. Now if you take that and you take the limit of t as it approaches 0, then you get the instantaneous velocity, which is dx of t dt, and that's going to be our equation number 1. Next we have the average velocity. In the same way we derive the average velocity, except we're going to use v of t minus v of t sub 0, which gives us delta v over delta t. We take the limit again here, and as t approaches 0, then we end up with dv of t dt. That's equation number 2. So now we need some general equations. The previous equations are first order differential equations that can be solved. Solving the differential equations for the differential dependent variable will give us general expressions that can be used in problem solving. So I'm going to start with the acceleration equation. So that's equation number 2. And so I have a of t equals dv of t dt. Now this is an instantaneous acceleration, and we will need an explicit functional expression for a of t. In many problem-solving cases, a of t will be a constant acceleration that does not change with time. This simplifies our equation to a equals dv of t dt. So as you notice here, a is a constant here, whereas it's not a constant here, it's instantaneous acceleration. So next we'll begin with solving that differential equation. And so we anti-differentiate both sides. Our next expression, we end up with this when we move dt over to the left-hand side. So next we use some placeholder variables. On the left side I used lambda. On the right side I used beta. And so you give it the appropriate limits of integration. And so I have a times t minus t sub 0 equals v of t minus v of t sub 0, and then finally I have v of t equals a times t minus t sub 0 plus v of t sub 0. That's equation 3. Okay, so the velocity equation. Since we now have an explicit equation for v of t, we can use this in equation 1 to solve for x of t. So going back to equation 1, we have v of t equals dx of t dt. And then we're going to begin solving for it. And so we have anti-differentiation. We have dt on the left side. And then when we put in what we just derived for v of t here, if we go back here, take a look at v of t, we're going to take that equation number 3 and put it in place. And now we end up with this expression. Next, we take that expression and we keep solving. We have this expression. Next, we put in some placeholder variables. I use lambda here, lambda there, beta here, epsilon there. Make sure that the limits of integration are appropriate. Okay, so next I have this expression here, a over 2 times t squared minus t sub 0 squared minus a times t sub 0 times t minus t sub 0 plus v of t sub 0 times t minus t sub 0 equals x of t minus x of t sub 0. And then next I have this expression where I just bring x of t sub 0 over to the other side and I isolate x of t. That's equation number 4. Okay, so now we can do some simplifications here. In the typical case, it is convenient to set the initial time t sub 0 equals 0 and x of 0 equals 0. This simplifies equation 3 and equation 4 to v of t equals at plus v of 0. That's equation number 5. And then we have x of t equals half at squared plus v of 0 times t. That's equation 6. So the concept here is that if you were to say, where does time start in this problem? Time can arbitrarily start at, 1, 2, 3, 5 seconds or whatever, but it's convenient that when you have the ability to arbitrarily start it where you want it to, it often makes a lot of sense to start it at 0. When you do that, then you make your problem more simplified. The same thing with x of 0, which is where does the initial position start. If you start it at 0, then it greatly simplifies your equations here, as you can see. So next, these are the constant acceleration equations that can be used in problem solving for kinematics problems. Now there's an additional equation that you'll see in textbooks, so you'll see this additional equation in books. This equation is derived from combining equation 5 and equation 6. So I'll take equation 5 and then I will reform it so that I isolate t. That gives me v of t minus v of 0 over a, and then I'm going to call that equation number 7. Next, I'm going to take that equation number 7 and place it into equation number 6. Then I end up with x of t equals half a times v of t minus v of 0 over a, all of that squared. And the same thing over here, I have v of t minus v of 0 over a, that being multiplied by v of 0. Next, I can factor out v of t minus v of 0 over a. Next, what I did here was, you can take notice here that these a's cancel out when you have a over a, that equals 1, so that cancels out. Next, what I have here is I distributed the half into these parentheses, and then you have half v of t minus half v of 0 plus v of 0. Then that's going to give you plus half v of 0 in here when these two are combined. Now I have x of t equals half v of t plus half v of 0. That's multiplied by v of t minus v of 0 over a. Then next what I did was to multiply 2a on both sides, and then that reduces the right side to this expression where I need to distribute my multiplication there. And so when I do that, I end up with v of t squared minus v of t times v of 0 plus the same thing, v of t times v of 0 minus v of 0 squared. So these two in the middle here, they cancel out. These second and third terms cancel out. And then I have 2a x of t equals v of t squared minus v of 0 squared. So then I just isolate v of t squared, and it gives me 2a x of t plus v of 0 squared. That's equation 8. So next I have my summary of constant acceleration equations, and I have v of t equals a times t plus v of 0. That's equation 5. Next, for position, I have x of t equals half a times t squared plus v of 0 times t. That's equation 6. Then next, I have v of t squared equals 2ax of t plus v of 0 squared. That's equation number 8. So you have one more case where you have 0 acceleration equations, and in the case that the acceleration is 0, which means a equals 0, the velocity is constant, and the constant acceleration equations simplify to v of t equals v of 0, x of t equals v of 0 times t. So if you go back here and you take a look at this, and you put 0 here for a, then all you're left with is v of t equals v of 0 here. And also if you put a equals 0 here, then v of t squared equals v of 0 squared. Apply a square root on both sides, and then you end up with the same thing. V of t equals v of 0, and that's that. Here, if you put 0 in place of a, then you're left with x of t equals v of 0 times t. So that's how you would get these two here, and you're left with this as expression. So that is all that I'm going to go over in these slides on how these equations for kinematics in physics books are derived. So hopefully this was helpful for you. Thank you for watching, and have a nice day.